Welcome to another episode of AI with Sally, an EE Times podcast that brings you inside my conversations with luminaries of the AI chip industry. Today's episode is brought to you by our sponsor, Sagence AI. AI chip startup Sagence AI has been working on bringing its unique flavour of analog compute to the market for some time. I had the opportunity to speak with Sagence CEO Vishal Sarin about why now is the right time for analog compute, thanks to a convergence of technology factors and market demand. In this conversation, we also speak about the challenges of product market fit for AI chip startups and what Vishal sees coming in the short and long term for analog AI silicon technologies. Here's my conversation with Vishal. Okay, Vishal, welcome to the show.
Thank you, Sally. Pleasure.
So you recently gave a terrific presentation at our EE Times The Future of Chiplets event. During your presentation, you were talking about AI as a breakthrough, just a huge breakthrough for the industry that really demands a breakthrough in supporting technologies, not just some incremental kind of improvements. Perhaps you could just set the stage for us by talking a little bit about what you mean by that. Why do we need a breakthrough at this point?
Yeah, certainly. AI, as in deep learning, is very compute intensive. And, what the industry had as we got through some of the early innovations, enabling lots of different things, both in vision and audio, and now in language models, was really built around the old paradigm of compute, which is essentially digital compute, starting off with CPUs, but folks soon realized that GPUs were giving a lot better performance for these kind of workloads. So that's where GPUs took off. But along the ways, the capabilities of what AI can do have increased manifold, as have the model sizes. They've gone up from the original sizes of a few million parameters to now hundreds of billions of parameters. You're talking 4 to 5 orders of magnitude larger models. What comes with that is huge, requirement for compute for AI, which is essentially drummed down to very specific compute, as opposed to just essentially matrix multipliers kind of at the core of it all, right? So innovations in software are speeding ahead of innovations in hardware. And the industry sees that, right? So really, what is happening is hardware is trying hard to catch up with the fundamentally same architectures and methods, but that leads to very high power consumption and very high cost of compute. And both of those are huge impediments for the industry, especially for mass adoption of all these models that are being built, because the focus was earlier on training, and now it's moving to inference, where you want to use these models for the masses, for so many other applications that are, it is enabling. But that requires us to manage power in a very substantial way, and to manage costs in a very substantial way. And the scaling, what's happening is models and their capabilities are growing up exponentially, but scaling in terms of hardware technology is just, on a linear path. So you see a huge disconnect there. And, I think we need a fundamentally new approach to computing so that we can fill that gap. And by the way, industry is looking at it from all angles, right? Industry is looking at it from software. How can we, try and manage it so that, we make it the sort of keep smaller models for specific tasks kind of approach, as well as try and reduce numerics that can help reduce compute requirements as well. But increasing problem, and it'll continue to increase as the capabilities grow. And I think we really need to kind of bridge the gap. So a new way of compute. The time is ripe for a new way of computing.
I agree, actually. But before we start talking about what the solution might be, I think it makes sense to just spend a moment talking about the problem. What is the real problem that we're trying to solve here? Is it about cost per token? Is it about performance, power, or something else?
Yeah, you could, for language models, right? For vision models, it's frames per second. For language models, it's tokens per second. But whatever might be a metric of performance, your performance metric, you have to be able to get more performance for less amount of dollar spent, because that is what is viable, economically viable for the masses in terms of using AI at a very fundamental level. So performance per unit dollar is a very important metric. Everybody's struggling from it. You've spoken to Microsoft, to OpenAI, Meta. It's a key component for everyone looking at this, which is why there are programs internally to develop silicon and try and manage that cost as much as you can. So that is a huge metric. The second one is performance per wattage of power consumed, because AI requires a lot of compute, and bigger models require larger amount of compute, and power consumptions are just going through the roof. Just by in another 2 years, about 40% of the data centers are expected to be starved from power, right? I mean, there's a lot of innovations that are happening in that regard, but it's a real problem because at a fundamental level, it affects our environment. No matter what, you have to manage the heat. We have a carbon footprint problem for humanity, and it's just just makes that worse by orders of magnitude, right? So this really needs to be solved at a fundamental level. Both of those metrics, performance per dollar from an economic point of view, and performance per watt from an environmental point of view, and also economics, because of course power means dollars as well.
Absolutely. How do you think the customer side sees these performance per dollar and performance per watt metrics? I don't necessarily mean the user. I mean the person that's buying hardware. Are they realistic about what they want and need when it comes to these types of metrics?
They are forced to be realistic because they really are wanting, in a very big way, better metric.
Yeah.
Better performance from each dollar they spend. It's a strong need for them. So then they have to go and look at other economic ideas on how to monetize all the spend that they're making. But it's a absolute need for the industry, and which is why a lot of innovation is coming forth. Necessity is a mother of invention, and so all of us are following what our mother wants us to do.
Okay. So talking about invention, I know at Sagence you're working on some analog type of AI. I think people who listen to this podcast are probably very familiar with the concepts of analog compute, which have been around in the industry for a really long time, or for a few decades at least. Can you tell us a little more about your approach to analog? I think from my perspective, there have been several companies in this space that have kind of tried and maybe failed. What's different about analog now, and what are you doing differently to succeed where other people haven't?
Yeah. So, to your point, analog compute or in-memory compute was thought about some 30 years back. And I looked at it back then as well as a concept, because it was really about mimicking the brain cells, which are analog, right? And the brain cells have essentially, the synapses in our brain have both compute and storage integrated into one unit. That's how the brain cells work. So, it really started from there, the very inception of AI. When we first started off, the memory technologies to do integrated storage and compute weren't there. The densities weren't there. The capabilities of what was possible was not in place, because the very low density memories were available, and so on and so forth. So the ecosystem was not in place to really, other than in the research labs, to really do this in a meaningful way and productize it for humanity, so to say. What's happened in the recent and over the last 10 years or so, also, companies have realized, IBM and others have really realized, HPI, all the companies, Intel, all of them have research work going on in this space, because the industry recognizes this is the right way to do compute, right? But a challenge that the industry always has is to really take something from the research lab, especially bigger firms, because they have their product lines. So how do you take management attention away from what is giving them billions of dollars today to something that is, that requires a lot of research dollars and also a lot of pain in terms of productizing research. But what's happened now, and why I think now is the right time, is that a lot of factors have come together to enable analog and memory compute, which is essentially what we do here is integrate memory and compute into one cell, just like the synapse of a brain, and use that cell and then try and make that cell as efficient as possible in the analog domain, so it is operating at really, really low energy levels, femtofarads, femtojoules, so to say. So that has come about now with the right kind of memory technologies available, which are capable of doing multi-level storage, as well as a lot of ecosystem that has developed around it. Quantization aware training used to be 32-bit floating point. Now inference is going towards 16, 8. So like I was saying, there's innovation happening on all ends to try and bridge the gap between compute and power consumption. Quantization, one aspect of it. So as you reduce from 32 to 16 to 8, you reduce your power consumption by half and you improve your compute by 2x. So these are things that are now coming together, which are just perfect for analog, because analog now, when you get to 8 bits and 4 bits, it's perfect for analog multi-level storage. So that's come about, right? It's perfect for inference. That's come about, right? All these tuning, AI/ML tuning methods for analog have come about in the industry. So all of these things are now happening at the right time, right place. So now is the time we have high density memories available. We have memories that are capable of multi-level available. We have quantization techniques available to quantize them down to 8 and 4 bits. We have AI/ML tuning algorithms available now that can tune and fit to smaller ADCs that were not possible earlier. All of these things have come together that now you have something that could only have been done in research labs to be able to now do it at scale and to productize it, which is very exciting because this is the new paradigm. The industry has recognized this for some time. It has to be done this way. It's just that people just didn't have the perfect storm.
The perfect storm
happening now.
Yes, I like that analogy. You mentioned quantization and tuning techniques. You mentioned memory technology and ADC technology. Another element in the perfect storm is chiplet technology, of course. I'm going to compare it to analog compute because, like analog compute, chiplets have been around for some time in some parts of the industry. This is already something that existed that's now finding new uses. Why do you think chiplets are such a critical part of this recipe?
They enable scaling out in a massive way for large deployments. And also they help build products that have heterogeneous integration, which is what you need because really, if you're looking at matrix multiplications, for instance, and you say, all right, analog in-memory compute is the right way to go. Multi-level is one step up above that. That's great if you can do that too. And deep subthreshold compute is another step up. That's what we do. Then if you can do that too, now you're in really, really, couple of femtojoules of energy consumption per compute operation. That then is amazing. But to enable that, you also want to maintain the flexibility of digital to be able to graph many different kinds of models that are coming about, which wasn't there with chiplet technologies. Enable us to disconnect the digital compute from the analog compute in integrated 3D packaging or 2.5D packaging, right? And what that does is, what the digital compute side does is, even though the requirement in terms of computability is low, it gives you a lot of flexibility because there's a lot of, like I said, innovation happening on the software side, new types of models and such, correct? So new kind of graphs, network graphs are coming about all the time. What the digital strength is flexibility in terms of modeling, mapping these graphs. analog strengths is doing one kind of compute in the most energy efficient way. If you can separate them out into different process nodes and into different packages, integrated at a chiplet level rather than on the same planar piece of silicon, you can take advantage of both. So now you've got scalability, you've got ability to map new and upcoming kinds of neural networks. You can still maintain very high power efficiencies, and you can scale out because the chiplet technologies themselves are having a perfect storm in the sense that the interposer sizes are growing. So you can accommodate more and more chiplets in a planar fashion, as is the 3D packaging. For the longest time, 3D packaging was stuck at, two chips in a package. And suddenly you see this all changing. Why? Like I said, it's necessity and the huge scope that it presents us with, right? And also, chiplets really allow you to innovate very quickly. Your innovation cycle becomes very quickly, because if you want to innovate on a new kind of model, but you don't need to change the analog portion, you just change that portion of the chip. So you change one small chiplet, and go on to the next product, as opposed to having to change an entire SoC, planar SoC, and characterizing it and all that, the cost and the resource that goes into it, right? So now you've made the whole problem very modular, very easy to integrate into many different kind of applications and edge use cases. So it's very critical, I think, for in terms of going forward as the models evolve.
As for Sagence, then, as a startup, being a chip startup is already a really tricky place to be because of the investment you need and the timescales you need to build a product, right? Do you think an industry-changing idea like the one we're talking about, bringing analog compute here, is something that can come from a startup? Or you touched on this earlier, maybe it's something that should come from a startup?
Yeah, the true industry, a lot of true industry-changing ideas come from startups. Actually, they incubate in companies like IBM and such, and in universities. But in terms of really taking them to productization and then, building a business out of it, a lot of that just grows from the startup, because there's a lot of pain, that's associated with a lot of, heartache that's associated with getting it all done and then productizing it and selling it and getting people to, accept what you're doing and so on and so forth, and then raising money along the ways. All of this is, part of the journey, which is challenging journey, and it's also fun. If it was too easy, it wouldn't be as much fun. So this is, I think the startups are the right place for them to happen, and that's where this is happening. That's where they are getting productized. They're leveraging on a lot of research. Startups are leveraging on a lot of research from the academia and from other companies as well.
So I think one of the biggest challenges with some of the AI chip startups that I work with, product market fit is a classic conundrum for a silicon startup, with AI in particular, because it just evolves so quickly. New algorithms are coming out all the time. How do you approach that with this 18 to 24 month design cycle that we have in the silicon industry? How do you specialize on the workload or not too much? How do you approach product market fit?
Yeah, so that's a very good question. And that kind of leads into what I was talking earlier, right? If you think about chiplets and you think about heterogeneous integration and you think about what it enables, what is it letting you do? It's, certainly product market fit, by the way, is really important. That's probably the holy grail of making a startup successful, because you don't have too many opportunities, right? One thing though, if you're developing a very differentiated technology, then the market gives you an opportunity to develop a new product, because now you've got something, a very core technology that can be then leveraged into many different, edge applications, end applications, and such. But the what I was talking about, the perfect storm in terms of what's coming about, with larger interposers and 3D packaging and so on and so forth, allows you to manage that long cycle in semiconductors that you have for development. Because now what you can do is you can say, hey, I want to go into cobots, and cobots requires one chip for my analog in memory compute, a small ASIC for the digital portion of it, and I need so much DRAM memory for it. So you can spin that out really quickly by just a quick integration on the board. You can do the same thing for humanoid robots. It requires a different amount of memory configured with compute. And as that changes, as the models change, and you realize, wait a minute, I need more memory for my in-memory compute portion, you can again leverage chiplets to have a quick spin around to follow those changes that are happening in the market from your customer point of view. So this is something that is very helpful. Chiplets in terms of managing that cycle time and also managing the resource and cost. Because if you don't have to spin, like I was saying earlier, you don't have to spin a full SoC 800 millimeter square die if you could just make your change on a 50 millimeter square ASIC and fit to a new paradigm of models coming about in the industry. So it's very exciting to see all of this coming together. Because not just AI, a lot that happens in the industry is ideas come about and contextual level and such in research organizations, and it takes several decades sometimes to really convert them into something that is productizable and scalable, and AI is just amazing in terms of what it's doing for us. So it's the scale out is potential is huge, right?
Yeah, very exciting. To continue with this theme of product market fit, for bigger AI applications, obviously they want you to supply a system of some kind, whether it's a small card, a big card, a server. Can you tell me a little bit about how you think about the system level or productizing at the system level, and what does system look like for you?
Yeah, we are. I mean, we mostly do our work with cards, right? Okay. We sell cards more than chips, so to say. And that is because we really want to pull together not just the core processor, but also the ecosystem around it to serve a particular application or a use case. The industry increasingly doesn't want to work with, we will do all the integration and such. Since the rate of change in terms of model innovation is very, very fast, the time that the customers want for you to come up with your solutions the turnaround time is very quick, very fast as well. So they really want to see a turnkey solution, so to say, right? So we really focus on looking at particular applications and then seeing what are the kind of models that those particular applications want, and what are the throughputs and the performance levels they want. What is the power consumption that can be accommodated in that particular use case, and what is the cost that can be accommodated? You can't build a system or put together a system that is costing you $500 and expect to sell it for $50 because it's going in a retail robot or something, which bill of materials itself is $50, right? So all of these axes of considerations when we build out the actual product for that particular end use case. And to that end, chiplets and having the modality, the modularity of being able to integrate into cards, different capabilities is very helpful.
Is there an element of wanting to control some of the system level or card level stuff? Obviously, if someone takes your chip and it's really fast and they put it in some server which is really slow, they're not going to get the performance they want. Is there an element for you of wanting to take responsibility for more parts of the system so you can ensure a good end result?
That is very true, because the more control we have over the full system, we can deliver a much better end result. And that has to do with the software as well. So we have our software tool flow. It's very much like TensorRT from NVIDIA, but we have our own processor. So we, of course, need a parallel flow to what TensorRT is. But we very much, would like to integrate that, because that really allows us, like you said, get the maximum out of our hardware.
Yeah, I mean, software is a huge, huge challenge. The AI software stack, especially for startups coming in, is a huge challenge. Can you tell me any more about how you plan to tackle that challenge?
Yeah, I can. So I love to talk about it because that's one of the things we did right. And I
Great.
think some of the earlier startups in the industry fumbled a bit. But you learn from other people's mistakes. That's always there. We really, what we did was we co-developed our hardware and software together. So it wasn't like the hardware was ready and the software wasn't. We modeled the hardware and we tested out our software as the hardware was being architected and as it was being developed. So that when our first product came out, it was fully functional, very first silicon. We'll be sampling with customers. And as well as the software was ready to map networks, we were mapping networks with our software stack that was in place as well. So that helped a lot. The second aspect of the hardware software is fundamental to our core technology. Because we integrate compute and storage into one unit, it allows the software to be simplified substantially. The best way I can explain that is your software does not have to deal with contention when, if you're moving data from storage to compute, it does not have to deal with contention because on the bus, on the data bus, because you have many, many compute units and many, many storage units, right? And then you have to manage those. Sometimes storage is available, compute is not, compute is busy, and sometimes there is contention between, your freeway, so to say, is too busy. We're moving other data through. So it's like, I say it's like when you're going for us, since it's integrated, it's like you're going from your home to and that helps with other parameters like latency. It's very important for certain applications, deterministic and very fast latency as well, right? So makes the software simpler, gives us very fast latency, very deterministic latency. Deterministic latency in the sense that you don't have any traffic lights when you're going from home to your office, so you'll reach it at the right time. But if you're going to have traffic lights because of the traffic patterns, sometimes you can get there in 20 minutes, sometimes it'll take you 30 minutes. So we don't have that problem or have much, less of that problem. And that comes from the fact at a very fundamental level, how we do compute. So our software, two aspects. One was, at the first place, it was simpler to work on. And secondly, we co-developed it with hardware. So that helped us a lot. But software always is, there's always a last mile problem with software. You're just trying to look at all the edge corner cases, making sure there are no bugs and so on and so forth. So there's a lot of reliability testing, so to say, in software.
Yeah.
Even when it's fundamentally working.
Yeah, so. Absolutely. Yeah, it's a huge task. Looking towards the future then, I know you said that analog compute is brain inspired, but when we talk about the brain, this is a 20-watt machine with 80 billion neurons. How close do you think we can get to what the brain does using analog technologies in silicon?
Yeah, a very good question. So, neuromorphics was an area which is really duplicating brain because it has time plasticity as well, which is how the brain cells kind of behave. So that's really the right approach. But the reason it's stalled a little bit is, again, just there are times for every technology. The training methods are a little different from, traditional deep learning training methods and so on and so forth. So the ecosystem required around it for software is a little different. And so, and industry does take that into consideration on ease of portability and use. But really that has, that's more like brain-like, so to say. We are on the deep learning side, right? So we are brain-like in the sense that just like synapses, we have memory and compute integrated into one, but we don't have time plasticity, right? We basically just giving vectors and multiplying them, just like in the digital compute side. Makes us very much like digital compute, but makes it a lot more efficient. So I think it's a step in the right direction. I mean, we make orders of magnitude improvement in terms of energy consumption. Now, brain-like would be another order or two of improvement that's required. So certainly we'll go there, and I'm sure someone will come up with solutions to handle that as well.
What about if we used emerging technologies like phase change memory? We have all kinds of exciting stuff happening in the industry. What role do you think emerging technologies play in analog compute, and which of these emerging technologies do you think you're most excited about?
So there are resistor RAM. Now, resistor RAM will, basically change the resistance, which is the same thing that you do with phase change as well. You change from crystalline to amorphous, and that changes the resistivity. Now, these technologies weren't, when we started off, they weren't prime time for mass production, yield issues and matters such as that. But they're coming about, and they don't have ability to do, there's some multi-level abilities that people have looked at in these, but I don't know how reliable they are yet for mass production. So my focus really was that, hey, if you're doing so much innovation, let's pull a technology that's been there for a long time, that's very stable, that has seen multi-level in mass production, because you will otherwise see production issues, reliability issues, and so on and so forth. Having lived this life for the last 30 years, you will see those problems when you go into production, in mass production. So let's just, look ahead a little bit, do something that is, that can be very reliable as a core technology. But having said that, both phase change and resistive RAMs I would say, are a little bit ahead of the curve. But both of them are very good technologies for analog in-memory compute. And some of the advantages they have is also the fact that they are scalable. Now, the good thing is, once you have chiplet technology, you don't need to scale for that much. You don't really need to scale, because all that required scaling and high, processing speeds was the digital nodes. Yeah. Or the digital nodes are separate. So you kind of scuttled the problem, walked around the problem, right? But certainly in this case, you can integrate the two, and then you can still scale. But then they're still not there where they can scale to 5. Like, we can use 5 nanometer digital, but they're still not there. They're 12 nanometer, 14 nanometer nodes kind of thing. Core technologies take time to mature.
Absolutely. I was going to ask what you see coming up in the long term for AI hardware, but I know this is a really tough question, because AI changes so quickly, of course, but hardware-wise, what do you see coming further down the line, like 5, even 10 years in the future? I guess you're a big believer in analog, obviously, but do you think ReRAM is where it's going to be?
So, no, not ReRAM. I think we are where it's going to be, frankly, because we have now decoupled the two, and we are using a very stable technology at a fundamental level. Flash has been around for 30 years. Now, the reason I'm saying that, if I see 5 to 10 years from now, the kind of benefit we can bring in orders of magnitude in terms of performance and normalized performance, you're looking almost at 10x lower power consumption, and at a system level. I'm not talking in chip level. For the compute level, we are like 2 orders of magnitude better, right? So these are huge benefits. So I think in a big way, analog will come in the next 5 to 10 years. And then to leapfrog ahead, I think we will have technologies such as neuromorphics. Now, whether they are built around core of optical compute or another kind of memory cell, and so that's up for grabs how that plays out. It could be resistive RAMs, for instance, for neuromorphics. I think that's a good chance. And optical is another one. Flash again is there. I mean, you can do that with Flash as well. But we are talking about I would say maybe after 10 to 20 years time frame for really mass adoption.
I think that's the perfect place to finish. Vishal, thank you so much. Thanks for joining us on the show.
It was a pleasure talking to you.
Thank you very much, Vishal, for the thoughtful conversation about analog computing and breakthrough hardware in the age of AI. This episode of AI with Sally was brought to you by Sagence AI. Thank you very much, Sagence, for sponsoring us. If you want to learn more about Sagence AI, please check the links on the podcast page at eetimes.com. That brings us to the end of the episode. Please tune in again next time for more conversations around AI silicon and systems. If you're listening to this on the podcast page at eetimes.com, links to articles on topics we've discussed are shown on your left. AI with Sally is brought to you by AspenCore Media. The host is Sally Ward-Foxton, our project manager is Colleen Heckman, and the producer is James Eade. Thank you for listening.